we were just working out a couple little examples here. I guess we just did one example of a particular graph conditioning on a particular set. And we looked at a whole bunch of pairs of nodes or pairs of random variables. And we checked to see if they're d-separated. And we found that, just by annotating this graph in a certain way, using these rules, by putting these little stop signs in the appropriate places, we could just immediately, just instantaneously, just by a glance, we could just immediately check whether a pair of random variables was d-separated. And remember, when they're d-separated, that implies that they are conditionally independent given C, given 3 in this case. But if they're not d-separated, that does not necessarily imply that they are conditionally dependent. So always bear that in mind. I'll keep harping on that so you never forget it. So let's do another example. Let's is so easy and fun. Let's do another one. Let's pick a different random variable to condition on. So let's redraw it, I guess. So let's redraw this thing here. So we've got maybe I'll pause so you don't have to wait while I draw this. Okay, I'll pause and be right back. Okay, we're back, and I finished drawing this graph. And now, so this is the same graph as before. And let's condition on something else. So let's condition now on, let's condition on 7. Condition on 7. So C now is, so before we had C was equal to 3, and now we're going to have C equal to 7. And let's see what happens. Let's write out a similar chart here. So we're going to consider we're interested in asking the question, is xi conditionally independent of xj given x7 now? So what is the chart? So we've got I, j, and we want to figure out if they are d-separated. So let's see. Is anything conditionally independent given 7? Well, let's see. Let's write out let's use our little rules here that we annotated this graph with these little stop signs. So let's do the same thing. See what happens. So we put a stop sign before if it was a tail at the conditioned on in a vertex. So if it was a tail at a vertex that was being conditioned on. So let's do that. Oh, well, there's none. There's no tails that are at 7. That's the thing we're conditioning on. And we also put a stop sign if it was a head-to-head place and the vertex was not being conditioned on and none of its descendants were being conditioned on. So let's see. So where are the head-to-heads? So here's a head-to-head. And it's not being conditioned on at 3, but 3 has a descendant, right? 7 is a descendant of 3. And it is being conditioned on, so we can't put a stop sign there. We only put a stop sign if it's not in C and no descendant is in C. So it's blocked only if it's not in C and none of its descendants are in C. But here one of the descendants is in C, so it's not blocked. Okay. What about this one? This is the only other head-to-head, I guess. And this one, it's the same situation. A descendant of 6 is in C, so it's not blocked, so we don't put a stop sign. So there's no stop sign. So nothing is conditionally independent given 7. Everything is, so nothing is conditionally independent given 7, or I guess given x7 to be precise. Nothing is conditionally independent, and we could just immediately read that off. No pair is conditionally independent, I should say. No pair. Well, that was cool. So let's do another one. Let me redraw this again, and we'll condition on something else. Let's do that again. All right, so I'll pause for a second here. Okay, we're back. So I made a copy of that same graph once again, and we're going to try something else now. So now let's try changing it. So we had 3 examples so far. We had one with this same graph, and let's call this maybe A. We had example B, and we could work out a whole bunch of cases really easily. And then we had example B, where we conditioned on something else. And then we're going to have example C. I hope I'm not confusing you with, this is not the sets A, B, and C. I'm sure that's clear. So this is going to be example C. And let's now change things up. Let's instead of just conditioning on something else, let's also change the game, and let's make it a let's change the graph to have an edge here from 1 to 5. So this will make things a little more interesting, because now we'll have to check more than one path. All right, so we've got that, and what should we condition on? Let's condition on 3 again. So that's the same as the first example, but now we have this new edge here from 1 to 5. So let's see what happens. So we're going to look at pairs I and J, and we'll see if they are d-separated. And so let's put in our stop signs here. So first, let's check head-to-tail relationships, or tail-to-tail. So we check the tails, and we only have to check the tails at the node which is being conditioned on. In this case, 3. So we need to put stop signs here and here. That's a bit overkill. Here and here. And then we need to have, at any head-to-head relationship, if that vertex and no descendants are conditioned on, then we put a stop sign between those heads. That's not the case here, but it is the case here. Head-to-head, C is not conditioned on, and none of its descendants are conditioned on. And those are the only head-to-head relationships. So let's see what happens here. So let's look at some pairs, maybe some pairs that'll be interesting. Let's look at 2 and 5. Are 2 and 5 d-separated given 3? Well, let's see. So 2 and 5, so in order to check if they're d-separated, remember we need to see if every path is blocked. Is every path from 2 to 5 blocked with respect to this condition set 3? Well, let's see. 2 to 5, so how can we get from 2 to 5? Well, we could either go 2, 3, 4, 6, 5, and that's blocked because it would have to go through both 2 stop signs, so that's blocked. And we also have to check, there's another path, 2, 3, 1, 5. 2, 3, 1, 5. And is that blocked? No, it's not blocked. So these are not d-separated. But so things have changed here, because 2 and 5 before, did we do 2 and 5 before? Yes, we did. We did 2 and 5 before, and they were d-separated because we only had this path, right? We only had the path going through here. Now we can go back up, and so, even though we're conditioning on 3, we can still pass through it here because this is a head-to-head. Okay. Let's look at another pair. Let's look at 2 and 7. Are 2 and 7 d-separated? So how can we get? So we can go 2, 3, 4, 6. But that's blocked. So that's to get from 2 to 7. We could also go 2, 1, 5, 6, 7. Okay, so we can do that. So again, these are not d-separated, right? We can go through here. We can go 5, 6, 7, because this stop sign only applies if we're going through the head-to-head. If we're only going from 5, 6 to 4. And let's do, maybe we do a couple more. How about 2 and 4? 2 and 4, we can't go that way. How about 2, 3, 1, 5, 6. Nope, can't go back up to 4 because we're blocked here. So that is yes. Right, so it is deseparated in that case because all the paths were blocked. 2, 3, and 4 was blocked, and 2, 3, 1, 5, 6, 4 was blocked at 6. So it is deseparated then. All the paths are blocked. And let's do 7 and 8. So this one might be interesting here. We have 7 and 8. Well, let's see. We can't go 7, 6, 4, 3, 8 because we're blocked at both of these tails actually here. So that would block us. And can we go around? 7, 6, 5, 1, 3, right, 1, 3, 8. We can't get back down to 8 because this is blocked. So, all right, I mean, you could just immediately see that since there's a stop sign at 8 here, we could, everything would be deseparated from 8. So that is also deseparated. So I think that I hope that this little trick, it can be very difficult to sort of just just sort of remembering these rules is I think the hardest part. And I hope that this little trick, I think that this is a neat little trick. Oops, using these little red stop signs to indicate or to annotate where you can't pass through is a really neat trick to be able to just immediately read off from the graph these deseparation properties. And then once you have that, then you can just, well, at least for the ones where it applies, then you know that they are conditionally independent, and so you can apply the theorem. You can apply the theorem in order to determine that they're conditionally independent. And of course, you could always do this same approach for sets, even though we were just looking at pairs of random variables and we were only conditioning on a single random variable. We could always extend this to sets and do the same exact thing, right? Because these rules here, these work in the same way for sets. It's just because the rules are applied. The fact that a particular path is blocked is only concerned with looking at a pair of random variables and looking at them being blocked at a single random variable. So all of this sort of little technique that we developed using these red dots and all, sort of visual annotating it and visualizing it this way, that all works just as well if we were considering sets of random variables. And the only difference is that you then have to check all the pairs of paths between, or all the possible paths between all the possible pairs of random variables in the sets A and B that you're checking for deseparatation between. Okay, so once again, I hope this was I hope you found this to be a useful trick, and hopefully this will help you to apply the deseparation property.